talk about Taylor series and Taylor polynomials. So you can see at the top of the page here, we have our standard formula for the Taylor series of a function f of x centered at a, f of a plus f prime of a, x minus a, etc. And then just a note here, in the second example in this video, we'll talk about Maclaurin series. So Maclaurin series is just a special type of Taylor series where the center number a is automatically 0. So if you're asked to put together a Taylor series, it'll either look like this first example here, so Taylor series for this function with this a value, or like the second example, they'll just say Maclaurin series for this function because the phrase Maclaurin series tells you the a is 0. Okay, so let's start this first example here. The first thing I'm going to do to start off this Taylor series is to just write out this standard formula with the a equals 1 filled in. So every instance of a up top, I'll put a 1. We can say f of x equals because this is equal to the function, or we can just put Taylor series equals if we'd like. So we'll have f of 1 plus f prime of 1 x minus 1 plus double prime at 1 over 2 factorial x minus 1 squared. And let's go one more to the 3 term here. And always, if it's a Taylor series, we end with a dot, dot, dot to imply that this pattern continues forever. Okay, so most of this Taylor series answer is what it looks like. What we are actually responsible for filling in here, specific to the function ln of x, is the f of 1, f prime of 1, double prime of 1, and so on. These derivatives with 1 plugged in are what we're responsible for actually computing and putting numbers in these spots. All the rest of it just survives until the final answer. Okay, so this means that we need to take a bunch of derivatives of this function. Again, for this example, I'm going to go all the way out to the term with 3s, so I'm going to go out to the third derivative for ln of x. All right, so if f prime is ln of x, or sorry, this is just regular f. Let's get rid of that prime. Right, so regular f of that is ln of x. Then f prime is 1 over x, which is x to the negative 1 power. So when we take the derivative again, that's negative x to the negative 2, or if you write that as a fraction, that'd be negative 1 over x squared. For all of these, I'm actually going to have both versions of the function because the fraction's easier to actually plug a number into, but the exponent is better for the derivative step. Okay, so third derivative, we have positive 2x to the negative 3, which would be 2 over x cubed. Okay, so for each of these, now we worry about what the center of this Taylor series is. So this is 1. So I don't need f of x, I need f of 1. So I'm going to plug 1 into this first function, and I get ln of 1 is 0. So that means this number right here is 0. F prime of 1 is going to be 1 over 1, which is 1. So that's right here. The next one, if I plug in 1, I get negative 1 over 1 squared. So that's negative 1 for this guy. For the next one, if I plug in 1, I have 2 over 1 cubed, which is 2. So that makes this one 2. And since this first term zeroed out, I want at least 4 terms in my answer personally. So I'm going to do one more step here. Take one more derivative. So the fourth derivative is negative 6x to the negative 4. Negative 6 over x to the 4th. So if I plug 1 into that, I will have negative 6. All right, so let's fill in what we have so far for our Taylor series. 0 plus 1 times x minus 1 minus 1 over 2 factorial x minus 1 squared plus 2 over 3 factorial x minus 1 cubed. And then I'll throw in the extra term that I created. We'll have minus 6 over 4 factorial x minus 1 to the 4th, and continue that forever. I can leave it here. This format is especially useful if I wanted to put this into sigma notation, for example. The only reason I would really want sigma notation is if they asked perhaps for the radius of convergence, something like that, I would need the sigma notation. Otherwise, you could start to simplify. So I'm going to give an alternative version of the answer with the 0 term just kind of dropped. 1 over 2 factorial is a half. 2 over 3 factorial is 2 over 6, so that's 1/3. 6 over 4 factorial is just 1 over 4. And we're starting to actually see a really nice pattern in these terms. So if I had to guess the next term, I would say plus a fifth x minus 1 to the fifth, and so on, which would make a really nice sigma notation formula. Okay, so typically on tests and quizzes, they're going to tell you exactly how many like non-zero terms to show in your answer. When in doubt, 4 is usually a good standard, which I have here. And we can also do spin-off examples related to Taylor polynomials. So Taylor polynomials are just the partial sums of a Taylor series. So if, for example, we were asked for the degree 2 Taylor polynomial for this function at this center, so the degree 2 Taylor polynomial, which we often call T2, I'm just going to take the terms of this series up until the degree 2 term, right? So T2 should be a degree 2 quadratic. So I'm going to go out to the quadratic term. And it's in kind of an unusual format. That would be T2. If I wanted T3, same thing. I would go all the way out to the degree 3 term. So once you have the Taylor series, then you can bust out as many Taylor polynomials as you would like. All right, my second example, as we saw before, is a Maclaurin series for cosine. And we want to remind ourselves when they say Maclaurin, the implication is that the A value in the Taylor series formula is 0. So that means we would have f of 0 plus f prime of 0, x minus 0, plus double prime at 0 over 2 factorial, x minus 0 squared, and so on. Okay, so in the next step, I'm going to do a couple of things. So I still need to compute all of my derivatives and plug in the center to turn these into numbers. But what I'm also going to do is take all of these x minus 0 terms here and here and here, and just write them as regular x. So this will be x, x squared, x cubed, and it'll just be that much prettier to look at. Okay, so again, we are plugging in for these numbers. So I want to go out to at least the third derivative of the given function and plug 0 into all of them. So here my f is cosine. Its derivative would be negative sine. Derivative of that is negative cosine. And then we go back to positive sine because we would have negative sine. All right, so let's plug 0 into all of these to get the numbers that go in these spots. Cosine of 0 is 1. Sine of 0 is 0. So I have 1, 0, negative 1, 0. So it's kind of good news and bad news, right? So we have half of our terms 0 out. This is a 1, a 0, a negative 1, another 0. But we have established a pattern, right? Because the next derivative in line after sine would bring us back to cosine, and we would repeat these numbers 1, 0, negative 1, 0 forever, because these derivatives will just loop. So I can extend this and still show 4 terms without doing too much more work. Okay, so we have 1 plus this 0 term, which I'll skip, minus 1 over 2 factorial x squared, plus this 0 term here. So that's this 0 from the list. So the next term, the coefficient would be positive 1. And it's the next term in the list here. So it's the one with a 4 in these two places. 1 over 4 factorial x to the 4th. And now we can kind of see this pattern starting. We're going to hit only the even numbers, and we're going to have alternating sign. Okay, the very last problem I have in this video is just a spin-off of the one before it, just for comparison's sake. So the example we just did is the Maclaurin series for cosine. So that's the Taylor series at 0. Now we're asked for the Taylor series of cosine at pi over 2. So same function, but a different center value of a. So that means I can reuse this structure with a pi over 2 instead of the zeros. But I have to redo all the stuff that I have in red here, right? So I can't actually reuse the rest of the work. So this Taylor series, or f of x rather, will be f of pi over 2 plus f prime of that, x minus that number, and so on. And now all I can really recycle from the previous example is the list of derivatives that I made, right? So these are the 4, and then after sine, it loops back to cosine. So whatever these 4 numbers are, it just repeats forever. So now I'm going to go back to this list and make a different list of plugging in pi over 2. So cosine at pi over 2 is 0. This is the top of the unit circle. The sine is 1, so f prime would be -1. Cosine back to 0. And then sine, we're at 1. So we have the same 4 numbers in a different order. Now it's 0, -1, 0, 1. 0, -1, 0, 1 would repeat forever. So those are what we're going to put in for our coefficients. So I have 0, -1, 0, and so on. And we put everything in their spots and get a completely different Taylor series. So I have -1 x minus pi over 2 plus a 0 term. So the next one that isn't 0 is the term with 3's in it. And its coefficient is going to be this 1. This is where we are right now. So we'll have plus 1 over 3 factorial with an exponent, of 3. And then the next one that'll show up is negative on the 5th. And so on. So we have 2 completely different Taylor series for the same function because we changed the center.